Let's take a look at this example, this physics example, where we connect derivatives to physics. And in this particular warm-up, you can see that we have been given a graph of the velocity function. So the first thing you want to pay attention to in these types of problems is what graph do I have? And a lot of times I will even come over here, even though it already has v of t on here, I'll just actually write the word velocity so that my brain remembers what kind of function that I'm looking at, because how I answer the questions is going to be dependent on what function I'm looking at. And this velocity function is indicating the velocity of a function of a projectile as it flies through the air on the closed interval from t equal to 0. So the graph starts here, information starts at 0 and 1, 2, 3, 4, and the information stops right here. Question A, when is the object rising? So I have to think to myself, I have a velocity function. What do I look at to determine, using a velocity function, when an object is rising? So I think to myself, well, if v of t is greater than 0, if the velocity is positive, then the object will be rising. If the velocity is less than 0, then the object will be falling. So that's what I'm looking for. So the first thing I'm going to look for is, where is velocity positive? So velocity is positive. I'm going to color it positive velocity here, positive velocity all the way to 4. So if I describe that region, the domain in which this object is rising begins at the x value of a. So the object is rising from a to d, and then the object rises again from g to 4. Notice that I close on the endpoint and I have opens on the intermediate points. Object is rising from a to d, object is rising from g to an x value of 4. All right, now the object is falling when velocity is negative, so velocity is negative here, velocity is negative here in the yellow zone. So the object is falling from 0 to A, open, and then again from open D to G, open at the intermediate values. All right, next question. When is the object stationary? So again, I have to think to myself, what would be true of velocity when an object is stationary? Well, that would mean that the velocity is 0. If the velocity is 0, the object is stationary. Stationary, not moving, no velocity. So I have to figure out when the velocity is 0. So if this is a velocity graph, the velocity is 0 at A, velocity is 0 at D, velocity is 0 at G. So object stationary when t equal A, t equal D, and t equal g. That's when the object is stationary. Letter C, when is the object moving fastest? Now this one you have to be careful of because this is a velocity graph. What would actually be most helpful is a speed graph. So we could create a speed graph. I'm going to erase what I've already done here once my eraser pops up. So let me clear this graph. So we have two choices, two ways to think about this. We can create a speed graph by taking the absolute value of velocity. Remember, speed is the absolute value of velocity. So then what I would do if I take the absolute value is that these negative regions would reflect, I should say, over the x-axis. So the graph would look something like this here when I reflect. So that little piece reflects. And then this piece right here would reflect upward. And so that's sort of what a speed graph would look like. So if I ignore everything down here, then I'm looking object moving fastest looks like out here at t equal to 4. That one's pretty obvious if this is t equal to 4. So the object is fastest at t equal to 4 because it asked me when is the object the fastest. Object is moving slower. Well, think about this. You can't move slower than not to move. So stationary is the slowest that you can move, not the negative region, but we're thinking about the speed. That's what fastest and slowest has to do with. So our answers for stationary, which we have right back here, t equal to a, t equal to d, t equal to g, that's when the object is moving its slowest. Now let's move the graph down and let's look at number 2. In number 2, we have the graph of a position function. So we have to make sure, it's kind of like an Etch-a-Sketch. You have to kind of clear your thoughts. We were thinking about how do I look at velocity. Now we're going to think about how do I look at position to determine, and again it's from 0 to 4, when the object is rising. Well, since I have a position function, that's easy. The object is rising when s of t is increasing. So if the position function goes up, then the object is rising. So I can see, starting at b, the object is rising, 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 rising. So I would say the object is rising from b to e on this position graph. So from b to e, the object is rising. The object is falling. It's a position graph, so it's falling when the position graph is falling or decreasing. So I'm looking for when the position graph is decreasing. So that would be from closed 0 to B, and from open E. Make sure you're choosing the X values and not the Y values. So from E to 4, even though I can't see it, I can see that the graph is continuing, well, sort of. The graph is decreasing. Next question. When is the object stationary? So I have to think to myself, what would a position function look like when an object is stationary? Well, it's still true an object is stationary when the velocity is equal to 0, but I don't have a velocity graph. So how would I figure out on a position function where the velocity is 0? Well, velocity is the slope of a position function. So I'm thinking about, when is the slope of a position function equal to 0? Well, that would give me, I'd be looking for horizontal tangent lines. And so I can see, I'm going to erase what I had here to just clean up my screen a little bit. As soon as, there you go, eraser. So I can see that there is a horizontal tangent line at x equal to b, horizontal tangent line, horizontal tangent line. So at these places, the velocity is 0. So I'm going to say object is stationary at t equal to b, t equal to e. Object is stationary because the velocity is 0. I see those horizontal tangent lines. Moving on, let's go ahead and answer the next. When is the object moving slowest? Well, still, slowest is to not move. That's the slowest that you can move. So the time when the object is slowest is the same as when is the object stationary. So at t equal to b and t equal to e. Now we have a position function and we're trying to determine when the object is moving fastest. So we still have to consider the idea of velocity, and we know that velocity is the slope of position. So if we want to find the fastest, what we're really looking for is the steepest slope of tangent lines. So we're kind of have to really think about our tangent lines and when would the tangent line have the steepest slope. So this is more of an approximation, so let me clear this off. And this is kind of not the easiest to answer. So I can see starting at 0 and stopping at 4. If I start at 0, the tangent line is pretty steep at 0, and it's getting, if you think about the tangent lines as pictures of tangent lines as I'm moving along, the tangent line is getting less steep because we're moving towards 0. So as I move away from 0, because down here, remember we said the slope of the tangent line down here is 0. So up here at t equals 0, at the time 0, That's a pretty steep tangent line, but as you move the tangent line along, they're getting less steep. So t equal to 0 is a candidate for the steepest tangent line. Then we have a slope of 0 down here at t equal to b. We have a slope of 0 at t equal to e. So slope of 0 in two different places. So think about this. We are moving away from a slope of 0 and getting steeper, and about halfway in between would be where we find the steepest slope, because as we continue moving, now we're moving back towards 0, so the slopes are getting less steep. So halfway in between B and E, halfway between B and D, sorry, I was right the first time, between B and E, sorry about that, would be a possible place where steepest. But I still think t equal to 0, if you look at the steepness, not the positive or negative, but the steepness, t equal to 0, so we are still a winner. So our candidates are t equal to 0, t equal to estimated about 1 point, I'll just say it's about 1.75. But I think this one is steeper. And then as I move away, I'm up here at 0, slope is 0, and as I start moving away, the tangent lines are clearly getting steeper and steeper and steeper and steeper. And at t equal to 4, which is not completely on the screen, it looks like I'm getting really steep. So I would say between t equals 0 and t equal to 4, t equal to 4 is going to be the steepest slope that I'm going to find, so I would estimate that the object is moving fastest at t equal to 4. So that's kind of an eyeball thing. That's not a clear question that I would ask you on an assessment, simply because you're estimating and you don't have specific values. All right, let's look at one more. I'm going to clear my annotations here. And in letter D, I'm going to move my screen down just a little bit to give myself a little room here to wiggle. So in letter D, we are going to try to sketch a possible graph of the velocity function. Now remember, velocity is slope of position. So we're going to have to analyze what the slopes are doing. So maybe over here I'll make a little chart, let's just keep it in orange, of what the slopes are doing. So starting at 0, we kind of already analyzed this. We said right here, the slope is 0. So we're going to start at t equal to 0, which is right here. And when I go up here, the slope at t equal to 0, if I draw that tangent line, it's very steep and it's negative. So at t equal to 0, the slope is negative. And as we move towards t equal to b, at t equal to b, the slope is 0. And then so from t equal to 0 to t equal to b, the slopes are, now think about this, if we're negative and we're moving towards 0, then that would mean that the slopes are actually increasing. So the slopes are negative and they are increasing. So when I try to sketch my graph, I'm going to go to t equal to b, and I'm going to put the derivative there is 0. We know that to be true because the slope of the tangent line is 0. We said in region 1, which is from t equal to 0 to t equal to b, the slopes are negative and they are increasing. So my graph might look like this. Slopes are negative and increasing until I get right there. All right, let's go to the next region, which would be from B, so starting right here, to halfway in between. Okay, that's like that 1.75 that I was talking about before. Now at t equal to b, the slope is 0. We already have that right here. And when we go to that next region, the slopes then, they're moving away from 0 and they're positive. So they are positive and they are increasing from t equal to b to this yellow point midway in between the valley and the peak. So positive increasing. So I'm going to continue my graph. So instead of making that look like it's turning, positive increasing. So I'm up to there, and I'm just estimating. Don't worry about the y values or how high or did I go high enough. It's the behavior that we're after. So we're here. Now moving into the next region from here to here, the slopes are still positive. Think about the tangent lines. The slopes are still positive, but now they're moving back towards 0. So in the next region, the slopes are still positive, but now those slopes are decreasing. So if I continue my graph in that region, the slopes are positive and decreasing. We know the slope at E is 0, so that's easy. So positive, decreasing. All right, so this was our maximum slope. So now we're going to go leave E where we have a slope of 0. The slope is 0 right up here at E. And now the slopes are negative as we think about the tangent lines, and they're getting more and more negative. So they're decreasing. So in that last region right here, the slopes are negative, and they are decreasing because they're getting more and more negative. And so the graph would look something like that. Now, if you think about it, I'm going to erase a little bit of this here. That makes perfect sense because the original function looks like it's a cubic function. The derivative of a cubic would be quadratic. So my graph seems to make sense that the purple graph would be a sketch, not the exact graph, a sketch of the behavior of the velocity function for this given position function.